Okay, welcome to the playlist for our AP Physics 1 Forces unit. Obviously we studied forces last year. They're probably even more fundamental to a good understanding of physics than kinematics is, because the study of forces is how we determine the rate of an object's acceleration in the first place, which then allows us to predict where that object is going to end up. So, the definition of a force, as you should know from last year, is very simple. It is just a push or pull on one object from another object. And that last part is very crucial. Force is really an interaction between two objects. There's never just a force that only that only comes from one object. Okay, it takes two objects to establish an interaction between them. That interaction is the force. Okay, so a force always is a push or a pull on one object from another object. As you know, a force is a vector, which means it has both magnitude and direction. The magnitude and direction are both important for describing the nature of the force. The units of a force are newtons, which is symbolized by a capital N. And as you remember from last year, 1 newton is equal to a kilogram times a meter over a second squared. Why is it equal to that? Well, we'll get into that when we talk about Newton's second law. Now, who's this Newton guy in the first place? Newton was born about 400 years ago. So we're, about 300, 350 years on from his life and what he was, famous for. And essentially, he was the founder, or the father of a lot of, what we would call modern physical science. Okay, natural. They used to call it natural philosophy back in the day, but we'll just call it physical science. He actually wrote the book that describes for us the rules, the physical rules of how motion works. For the most part, he didn't obviously describe everything. But he has the basis. This book, Principia Mathematica, is what he is most known for. And I shouldn't say that. The reason that book is so famous is because we get what are known as Newton's 3 laws from that book. Okay, they're postulated in the book, and they are extremely useful in describing how objects and forces interact. So, without further ado, Newton's first law, and I'm going to paraphrase just a little bit. Newton's first law says that an object that is at rest or in motion will stay that way unless acted upon by an outside net force. So, what this means is an object that is at rest will remain at rest unless acted upon by an outside net force. An object that is in motion will stay in motion unless acted upon by an outside net force. So, the conclusion you're supposed to draw from this is that it takes a net force to change whatever an object, the state of motion of an object. If an object is at rest, it takes a net force to make it not at rest. If an object is in motion, it takes a net force to change that type of motion. Not necessarily bring it to rest, but to just change that motion. In other words, speed it up, slow it down, make it change direction. Example. Take a look at this calculator right here. This calculator is on the table, or on my little ring stand. And very clearly right now, from our perspective, it is at rest. Okay? So it is not going to start moving, until some other object puts a force on it, causing a net force, which leads to it moving. Now, obviously, there are two interactions that are going on right now with this calculator. You could say, well, wait a sec, it's interacting with an object right now. It's interacting with the stand. It's also interacting with the Earth. The stand is pushing up on the calculator. Earth is pulling down on the calculator. yes, that's true. Both those objects are exerting forces on our calculator, but that is being done in such a way that there is still no net force. And we'll talk about what net force means. You should remember that it means the sum of the forces. Okay, there is no net force now. Now, if I were to come along and put another force on it, okay, that caused there to be momentarily a non-zero net force. There was a net force. So that caused that motion. Okay, that caused that change in motion from at rest to moving. Another example, and people don't usually think of this one, but it's kind of the opposite. Let's say that you have a spaceship, and that spaceship is cruising through deep space. Deep space here meaning there are no planets near, there's no galaxies, there's no stars, there's nothing, the force of gravity from these other objects, even though it's not zero, is negligible. Okay, cruising through deep space with no engine firing. So it is just gliding there. The engine is not firing or anything. What's going to happen to this? Well, it will continue to move. Continue to move forward, or whatever way it was moving, at a constant rate, meaning a constant velocity, until something else either pushes or pulls on it, which would create a net force. Okay. Now, this goes against what one of the most famous thinkers in Western history, Aristotle, would have said. Aristotle was a famous philosopher back in ancient Greece, and what Aristotle essentially said was that the natural tendency of anything is to be at rest, which makes sense. Usually, objects are at rest. Motion is a little bit different. Aristotle would see objects, take for instance, let's say something sliding over the ground. Okay, it was moving, but then it stops. So Aristotle kind of, it makes sense that he said that, the natural order of things must be to be at rest. Motion is just a brief interruption in this. Now, that's not accurate. Okay, Aristotle, what he was seeing was an object being affected, obviously, by friction. And when he saw that object being affected by friction, it's very hard to tell when friction acts on something if you don't know that there is friction. Imagine if Aristotle had seen an object traveling over a long strip of ice, or something else that's very, very frictionless. He might not have had that thought, because that object would not have changed its motion as it goes over that ice, perhaps. Greece is a little warm, there's probably not big strips of ice anywhere, but to me, it's kind of interesting to think, what if Aristotle had been born up in, I don't know, Norway or in the Arctic Circle? Would he have come to the same conclusion after seeing objects that have, that go over very, very low friction surfaces? I don't know. In any case, just as an object that is at rest won't start moving until a net force acts on it, an object that's in motion will not change its motion unless a net force acts on it. So this spaceship cruising in deep space, there are no forces on it, essentially. We can neglect them. It's so far away that those forces are very small. It's going to keep doing whatever it's doing until something pushes or pulls on it. So until some other object gets there and starts exerting a force on it. Okay? And that is 100% accurate. There is no, that spaceship would just keep going. Okay, it would never ever stop until something else went along and affected it. So that's Newton's first law. A lot of times people they can parrot that one back very easily. It's a very famous law, but they don't really understand what it means. Or if I ask them a question, asking them to apply Newton's first law, they would get it wrong. Okay, the only way to change the state of an object's motion is to apply a net force to it. If there is no net force, the object's motion doesn't change. Okay, that doesn't mean it doesn't move, or it means that the motion itself does not get altered. If it was at rest, it's going to stay at rest until a net force acts on it. If it was moving, it's going to stay moving. Newton's second law is the one that I like to refer to as the equation one. It's got the equation in it. Newton's second law says this, and really it kind of makes sense if you understand what we were just talking about with the first one. Newton's second law says that the net force that acts on an object is equal to the object's mass multiplied by the acceleration that the object therefore experiences. Now, you might also see it this way. Instead of writing F net, you might see this kind of funny looking E thing. F equals ma. That's just the Greek capital sigma. That's a Greek letter. And all it means is the sum of the forces. That's what net force is. Net force means the sum, the addition of all the forces. And we just talked about how to add vectors, and forces are vectors, in the last unit. So think of it as we're adding all these vectors together to figure out what the acceleration of the object should be. Let's talk about a couple different scenarios here. What happens if the net force is 0 newtons? Oh, and by the way, if you want to know why a newton is equal to a kilogram times a meter per second squared, look at the units here. F net, that's a force, is measured in newtons. Mass is measured in kilograms. Acceleration is measured in meters per second squared. So if we multiply kilograms times meters per second squared, we get this, which must be equal to 1 newton. A newton essentially is just an easier way of saying a kilogram times a meter per second squared. Anyways, back to what we were doing. If F net does equal 0 newtons, then what that means, one way to describe that is that the forces are balanced. There is no net force, which means there is no acceleration. To see why that is, imagine that you plugged in a 0 for the net force. That means something on this right-hand side must be 0, since you have two things multiplying by each other. The only way to take something and get 0 from multiplication is if one of those is 0. If we're talking about an object here, all objects have mass. They're made up of matter, and matter is what contributes to mass. So if F naught is 0, m probably isn't 0, since we're talking about an actual object. Therefore, a must be 0. There's no way to take any non-zero number for a, multiply it by another non-zero number for m, and get 0 out. The only explanation is that the acceleration must be 0. So there's no acceleration if there's no net force. If F naught is 0, a is 0. Because there's no acceleration, acceleration is the rate of change of velocity. If the rate of change is 0, that means we have a constant velocity. Which means we have no change in the object's motion. The object is in what we refer to as equilibrium. Okay? All 5 of these terms are all linked together. They all essentially mean the same thing. If there is no net force, there is no change in motion. The object is therefore in equilibrium. It's moving at a constant velocity, which could be 0, it could be stopped, or it could be moving with a constant velocity, and there's no acceleration. All 5 of those things always come together. If F net is not 0 newtons, then we have the opposite. We have forces that are unbalanced. And as I point this out, when I say balanced, we don't mean that there are no forces acting on the object. The forces just balance each other out. Perhaps you have forces of 50 newtons, but in exactly opposite directions. In that case, the net force would be 0. So if the net force is not 0, the forces are unbalanced, which means there is a net force, and therefore there is an acceleration. There is a change in velocity that is not 0 meters per second, and the motion changes. And we have no equilibrium. Let me just add a couple of examples here. An example of net force of 0 would be like a hockey puck on frictionless ice. Regardless of if it's moving or not, actually. Long as nothing else is touching the hockey puck, as long as like the person's not pushing it with a stick, if that hockey puck is just gliding over the ice, even though it's moving, if it's gliding at a constant velocity and friction is truly 0, then the net force is 0. Even though it's moving, you can have a net force be 0. There's well, actually, I'll wait to get into the types of forces, but that would be a situation where the net force is 0. The object remains at a constant velocity. As far as an example where the object does not remain where the net force is not zero. Imagine stepping on the gas in a car. Okay, you're allowing there to be a net force on the car. It's a little complicated how the net force gets on the car in the first place, but you're allowing a net force, you're allowing acceleration, the velocity, the motion are changing, you're not in equilibrium anymore. Okay, and we'll do lots of examples in class to show whether something is in equilibrium or not in equilibrium. Let's talk really briefly about Newton's third law as well. Newton's third law is another one that's a famous statement that a lot of times I don't think people truly understand. Newton's third law says the following. Every action, and I'm just going to put in parentheses here what an action means. Newton by this meant a force. Every force has an equal and opposite reaction. And by that, he means, again, force. Okay? This is easily the most misstated out of all of Newton's laws. I've heard people say that this law is the same thing as saying what goes up must come down. Not at all. It has nothing to do with this. I've had people say that this explains why you always need two forces in opposite directions on an object. That is totally not true. What this really refers to is that when forces are interactions between objects. When one object exerts a force on another object, the second object also exerts a force back on the first object. So in other words, another way of saying this is if you have two objects, A and B, object A exerts a force on object B must be exerting a force back on object A. To give you an example, if I push down into this paper, not only am I pushing on the paper is also pushing back up on me. You can try this also. My favorite example of this is if you push on a wall, okay, the wall actually pushes back on you. That's how if you push off of a wall, that's why you move away from the wall, because the wall is literally pushing on you. You are pushing on the wall, and the wall is pushing back on you. So example, you push on wall, I just spelled wall wrong. The wall pushes back on you. Okay? And when we say equal and opposite, the force that you exert on the wall is exactly the same as the force the wall exerts back on you. It just happens to be in the opposite direction. How I would symbolize this is the force from you on the wall is equal to the negative of the force from the wall on you. Now, why is the negative there? Because they're in opposite directions. If I were to take the absolute magnitude of this equation, I would see that both sides are exactly the same. The only difference is there's a negative sign. So, this is a case where we have forces that are equal in magnitude, but opposite in direction. Okay? Now, briefly, we're going to talk very quickly about some types of forces. We'll finish up the types of forces in the next video, but let me at least get a few of these forces down. Types of forces with symbols. One of the most common ones, one of the first ones you learned about last year, is the force of gravity, or the weight. They mean the exact same thing, okay? These symbols stand for the same thing. It's like calling me either Mr. E or Mr. Isinger. It's the exact same thing, okay? Force of gravity, or weight. You actually learned two equations for this last year. Last year you learned this equation, Fg equals mg, which I like to say this equation is used for everyday objects, where this little m is the mass of the object you want to know the weight of, and g is the acceleration due to gravity. And that will change depending on where you are. If we're on Earth, remember we use approximately 10 meters per second squared for Earth. Okay, last year you used 9.81, this year I'm allowing you to use 10. What if you're not on Earth though, and you don't know what the acceleration due to gravity is? Newton actually came up with a law, an equation, that shows us how to calculate the force of gravity, even if you're not on Earth. And that equation is as follows: G, little m, big M, over r squared. Okay? And again, this is used for primarily big objects in space. All right, so most of the time we're going to end up using this equation, but on occasion we will have to use this equation. And just some symbols breaking down what they are. Little m and big M are masses. Big G is what is known as the universal gravitational constant. And that is on the front of your reference sheet this year. It is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Little g is the acceleration due to gravity. Which we're going to say is 10 meters per second squared on Earth. And then r is simply the distance between the objects. Distance between objects. Okay? So one last thing about this equation, I usually think of it as, since we're always talking about force being an interaction between two objects, this equation over here is the equation that you use to figure out the force of gravity between any two objects. This equation here is where you would use it's how you would determine the force of gravity between one object and a much bigger object, such as Earth. You can use either equation if you have enough information, but this is for any two objects ever. One of them does not have to be a big object like Earth, could be like my pen and this calculator. This equation is typically used for if you're on the surface of a planet and you want to know the force of gravity between that planet and the object. When we come back, we'll talk about 5 more forces or so, and then we'll move on to free body diagrams.